Hello students, today we'll discuss about the capacitance. So here you are observing the figure. So here M1 is the conductor and M2 is the conductor. So now let us consider two conductors embedded in homogeneous dielectric, right? So here dielectric is there in the homogeneous dielectric. Okay, so M1 conductor and M2 conductor. Now conductor M2 carries a total positive charge Q1 and M2 carries an equal negative charge minus Q. Now no other charge is present, so the total charge of the system is 0. Okay, so therefore charge is carried on the surface as the surface charge density. The electric field is normal to the conductor surface. Each conductor is an equipotential surface. Okay, so here you can see by seeing those points we can tell that capacitance is considered. You can evaluate the capacitance by considering the two conductors, right? So here capacitance so now next what we can have is the electric flux is directed from M2 to M1, so thus M2 is at more positive potential. Now works must be done to carry a positive charge from M1 to M2, right? So let us assign a V0 as a potential difference between M2 and M1. So we may define the capacitance of these two conductor system as the ratio of total charge on either conductor to the magnitude of potential difference between the conductors. So to define what capacitance, we need a charge on both the conductors, that is Q1 and Q2, and also we need to assign a potential V0 to move the charge work done from positive charge to move from M1 to M2. And also capacitance, we can write it as integration over surface epsilon E dot ds. This is for charge, and V0 you can write it as minus of integration over minus, lower limit is minus, upper limit is plus, so E dot dl. So this is the equation of a capacitance, right? So how we can define a capacitance. Now capacitance is independent of potential and total charge, for their ratio is a constant. So because it does not dependent on what charge and this one potential, because its ratio is constant. So if the charge density is increased by a factor, Gauss law indicates that electric flux density or electric field intensity also increases by same factors as does the potential difference. So this is one thing you can tell by a Gauss law. The capacitance is only the function of physical dimension of the system of the conductors and permittivity of the homogeneous dielectric, right? So it does not depend on what is the charge, and it does not depend on what is the potential, but it depends on the physical dimension of the system conductors, and it depends on the permittivity of the homogeneous dielectric. Now capacitance is measured in farads. 1 farad is equal to 1 coulombs per volt. Okay, so next we'll now apply the definition of capacitance to the simple two conductor system, where the conductors are identical. Infinite parallel planes and separated a distance d from to each other. Now you can see here one is a conductor surface with a minus rho s, and one more is you can have this plus rho s conductor surface. So uniform surface density will have around this. Now z is equal to 0 plane and z is equal to d here. Electric field intensity is having upward in the upward direction. Now E is equal to what here? We can tell rho s by epsilon az. Electric field intensity for such a parallel conductors is nothing but E. This much is given. So D is equal to rho s az. Now the charge on the lower plane is positive since d is upwards, so hence dn is equal to dz, there is nothing but plus rho s. The charge on the upper plane is negative, so dn is equal to minus dz, that is nothing but equal to minus rho s, right? Now the potential difference between lower and upper plane is v naught is equal to minus integration over upper and lower limits, so E dot TL, that is nothing but equal to integration of minus integration of upper limit is d and lower limit is 0, epsilon rho s by epsilon into dot dz. So this will give as a rho s by epsilon d after integration. Now total charge for an area S of either plane, both with a linear dimension much greater than opposition d, is q is equal to rho s s. So the capacitance of a portion of infinite plane arrangement from the edges is c is equal to q by v naught, that is nothing but equal to epsilon s by d. It's nothing but equal to epsilon s by d. So you can write q as epsilon s by epsilon s and v naught as a d, right? So we'll see one of the problem on the capacitance. So this is how what we all discussed about the capacitance. So we can have the two equations here. One is what you can get c is equal to q by v naught, and this one equation in terms of integral form, and you can have measure the value of E and D in terms of capacitance, and also we can have we can tell that v naught, the value of v naught and the value of q, and by placing them we will get this value of C capacitance. So therefore we consider one of the example here. Calculate the capacitance of a parallel plate capacitors having a mica dielectric. Epsilon r is equal to 6, a plate area of 10 inch square, and a separation of 0.01 inch. So therefore here we need to calculate the capacitance of a parallel plate capacitor with a dielectric of epsilon r is equal to 6, area is 10 and the separation is 0.01. so area you consider, so here we are having an area in terms of 10, and we get a capacitance equation as epsilon s divided by d. So we need to multiply this 2.54 into 10 raised to minus t minus 2 for converting it into meter. So here 10 into 2.54 into 10 raised to minus t, so it is converted as 6.452 into 10 raised to minus 2 meter 10 raised to minus 3 meter square. Now d is also you have to convert in meter, 0.01 inch into 2.54 into 10 raised to minus 2. So put the value of s and d, where epsilon is given as 6, so 6, and the value of this is s, and this is the value of d. So epsilon naught is 8.854, epsilon r is 6. So therefore the value of capacitance will get it as 1.349 nanofarad. So this is what one of the example of capacitance of parallel plate capacitor, S D. So this is the equation of capacitance, right? Next, along with this, we can also calculate the total energy stored in the capacitor. So here WE is equal to half of integration of volume epsilon E square dV. So half integration of volume epsilon E square can be written as rho s by epsilon square into dV. So half of integration over 0 to s limits and 0 to d limits, one more integration, rho square by epsilon dz ds. So after integration we will get half of rho s square by epsilon s d, and this is again further written as half of epsilon s by d into rho s square by epsilon square d square, right? So here we can write W is equal to half of C and V naught square it is, and we get as a what, or you can write it as half of Q V naught, or it can be written as half of Q square by C. So therefore C is equal to uh, epsilon S by Vd, epsilon S by D, and V naught is OS epsilon, or OS by epsilon into D, and C is equal to Q by V naught. This is all about the capacitance and one problem on capacitance, and also we have derived the equation of total energy stored in the capacitor. Thank you.